We abandoned the moon. 12 people walked on its surface, and then we vanished for 50 years. No missions, no footprints, just silence. Today, we're diving deep into the real reason we abandoned the moon and what it tells us about our place in this vast universe. And here is a question for you. If you could break one law of physics for a day, which would it be? And what would you do? Share your wildest idea in the comments. I'll pin the most creative answer. Now let's begin. Let's rewind to December 14th, 1972. Commander Eugene Cernan, the last person to walk on the moon during the Apollo 17 mission, prepared to climb back into the lunar module. His final words on the lunar surface were poetic and hopeful. We leave as we came, and God willing as we shall return, with peace and hope for all mankind. He knew that Apollo missions 18, 19, and 20 had already been cancelled, but I doubt he imagined his footprints would remain untouched for over half a century. Those words, spoken in the stillness of the lunar vacuum, became a time capsule of optimism, a promise, a contract with the future. Except we broke that contract. Think about it for a second. In just 8 years, from 1961 to 1969, we went from barely launching humans into orbit to landing them on another celestial body. 8 years. That's less time than it takes some construction projects to finish. The technology was primitive by today's standards. The computers guiding the Apollo spacecraft had less processing power than your smartphone. Yet we did it. So why, with all our advanced technology, artificial intelligence, reusable rockets and supercomputers, haven't we done it again? The first answer most people jump to is money. And yes, cost plays a massive role. The Apollo program, adjusted for inflation, cost around $280 billion in today's money. That's an astronomical sum, no pun intended. But here's where it gets interesting. We didn't stop because we ran out of money. We stopped because we ran out of reasons. Let me explain. The space race wasn't really about space. It was about something far more earthly: politics, power, pride. In the 1960s, the Cold War between the United States and the Soviet Union was at its peak. When the Soviets launched Sputnik, the first artificial satellite in 1957, it sent shockwaves through America. Then came Yuri Gagarin, the first human in space, in 1961. The message was clear: the Soviets were ahead. And in the context of the Cold War, being ahead in space technology meant being ahead in missile technology. It meant having the power to strike anywhere on Earth. President John F. Kennedy understood the stakes. In 1961, he made a bold declaration. America would land a man on the moon and return him safely before the decade was out. This wasn't just about exploration. It was about demonstrating superiority, proving that American ingenuity, freedom, and capitalism could outpace Soviet collectivism. The moon became a stage and the whole world was watching. And when Neil Armstrong took that first small step on July 20th, 1969, it was a victory lap for the United States. The Soviets never landed a person on the moon. The race was over. America had won. So what happened next? Without the urgency of competition, political interest faded. Congress started asking tough questions. Why are we spending billions on moon rocks when we have problems here on Earth? Poverty, inequality, the Vietnam War. These were pressing, visible issues that demanded funding. The moon suddenly seemed like an expensive vanity project. By 1972, 3 Apollo missions had been cancelled. The Saturn V rocket, the most powerful machine ever built, was retired. The infrastructure, the expertise, the momentum, all of it was dismantled, not because we couldn't go back, but because we chose not to. Here's the thing that blows my mind. We threw away the blueprints. Well, not literally, but close enough. The knowledge and industrial base required to build the Saturn V rocket faded away. The engineers retired, the factories closed, the supply chains vanished. By the time we wanted to return to the moon decades later, we had to start almost from scratch. Imagine building the most incredible machine in human history, using it a few times and then saying, "Okay, we're done, let's move on." That's essentially what happened, but the story doesn't end there. In the decades that followed, space exploration shifted. The focus turned to low Earth orbit. We built the Space Shuttle, a reusable vehicle designed to make space access routine. We constructed the International Space Station, a marvel of international cooperation orbiting just 400 kilometers above us. We sent robotic probes to every planet in the solar system, landed rovers on Mars, and flew past Pluto. We learned to explore without risking human lives, and we learned to do it cheaper. The Moon? It sat there, quietly waiting. Fast forward to today, we're on the cusp of a new era. NASA's Artemis program aims to return humans to the Moon, and this time the goal isn't just to visit, it's to stay, to build a sustainable presence, to establish a lunar base. Artemis 2, scheduled to launch in April 2026, will send 4 astronauts on a flyby around the Moon. It's the first crewed mission beyond low Earth orbit since Apollo 17. The excitement is real, but so are the challenges. The Artemis program has faced delays, technical setbacks, and budget overruns. The Space Launch System rocket, NASA's new heavy-lift vehicle, has been criticized for its cost and development time. Some say it's taking longer and costing more than the original Apollo program, and they're not entirely wrong. If you're enjoying this deep dive into space exploration and want to understand more about the challenges we face beyond Earth, make sure to hit that subscribe button and give this video a thumbs up. Your support helps me bring more cosmic stories to life. Seriously, it means the world to me. So why is it so hard to go back? One reason is that we're trying to do it differently this time. Apollo was a sprint. Artemis is a marathon. Apollo was about planting a flag and coming home. Artemis is about building infrastructure, a lunar gateway, a small space station orbiting the Moon, habitats on the surface, nuclear power systems, pressurized rovers. This isn't just a visit, it's the foundation for a permanent human presence, and that requires a completely different approach. More technology, more testing, more time. Another challenge is safety. We've learned a lot since the Apollo days, and not all of it makes us more confident. We know more about the dangers of space radiation now. We understand how cosmic rays and solar particle events can damage DNA, increase cancer risk, and harm the central nervous system. The Apollo astronauts were lucky. Their missions were short, just a few days on the lunar surface. They avoided major solar storms, but if we're building a base, if people are going to live and work on the Moon for weeks or months, we need better protection. We need shielding. We need radiation shelters. We need to solve problems that Apollo never had to face because those missions were too brief. Then there's the dust. Lunar dust isn't like beach sand. It's sharp, abrasive, and electrostatically charged. It sticks to everything. It got into the Apollo spacesuits, the equipment, even the lunar modules. It caused wear and tear on seals and moving parts. Armstrong and Aldrin were only outside for a couple of hours, and the dust was already a problem. Now imagine months of exposure. We need new materials, new designs, solutions that didn't exist in the 1970s and still don't fully exist today. And let's talk about the rocket itself. The Space Launch System is powerful. It generated 8.8 million pounds of thrust at liftoff during its uncrewed test flight in November 2022. That's more than the Saturn V, but it's also expensive. Each launch costs around $4 billion, $4 billion for a single flight. Critics argue that commercial alternatives like SpaceX's Starship could do the job cheaper and more efficiently. Starship is designed to be fully reusable, which could dramatically reduce costs. But it's still in development. It's had test flights, some successful, some explosive. The technology is promising, but it's not proven yet. NASA is betting on multiple approaches, which is smart, but it also means coordination challenges, delays, and complexity. Here's something fascinating. The Artemis program isn't just about returning to the moon, it's a stepping stone. The real target is Mars. Everything we learn on the moon, how to live off Earth, how to use local resources, how to protect astronauts from radiation, will apply to the red planet. The moon is close. If something goes wrong, help is only a few days away. Mars is a different story. A one-way trip takes 6 to 9 months. Communication has a delay of up to 20 minutes. If something breaks, you're on your own, so the moon becomes a training ground, a proving ground, a place to make mistakes and learn before we take the leap to Mars. Speaking of Mars, the challenges of living on another world are staggering. If you want to understand just how hostile Mars is and why humans might never be able to truly colonize it, you should check out my video called "Why Mars Will Always Be Lethal for Humans." It goes deep into the radiation, the toxic soil, the lack of a magnetic field, and all the hidden dangers that make the red planet far more dangerous than most people realize. I'll leave a card up here so you can watch it after this one. Trust me, it'll change how you think about becoming a multi-planetary species. But let's get back to the moon. There's another layer to this story that doesn't get talked about enough: international politics. The space race of the 60s was a two-horse race, America versus the Soviet Union. Today it's far more crowded. China has an ambitious lunar program. They've landed rovers on the far side of the moon, something no one else has done. They're planning crewed missions. They're talking about a lunar base. India landed a spacecraft near the lunar South Pole in 2023. Private companies like SpaceX, Blue Origin, and others are entering the arena. The moon is becoming geopolitically significant again, not because of Cold War rivalry, but because of resources, strategic positioning, and prestige. Water ice, that's the key. Scientists believe there are deposits of water ice in permanently shadowed craters near the lunar South Pole. Why does that matter? Because water is everything in space. You can drink it, you can split it into hydrogen and oxygen for rocket fuel, you can use oxygen for breathing. If you have water on the moon, you don't have to bring it from Earth, which saves massive amounts of weight and cost. Whoever controls lunar water could control the future of space exploration. That's why Artemis is targeting the South Pole. That's why China is interested in the same region. The moon is becoming a strategic asset. Now let's zoom out for a second. Why should we care? Why does it matter if we go back to the moon or not? These are fair questions. Some people argue that we should focus on Earth. Climate change, poverty, disease, these are urgent crises. Spending billions on moon missions seems indulgent, even reckless. I get that perspective. But here's another way to think about it. Space exploration drives innovation. The technology developed for Apollo gave us everything from integrated circuits to cordless tools to water purification systems, memory foam, scratch-resistant lenses, freeze-dried food. These weren't the goals of the program, but they were the byproducts. When you push the boundaries of what's possible, you create solutions that ripple outward into everyday life. More than that, space exploration changes how we see ourselves. The Apollo 8 astronauts on their journey around the moon in December 1968 took a photograph called Earthrise. It showed our planet rising above the lunar horizon, a fragile blue marble suspended in the black void. That image helped spark the environmental movement. It reminded us that we share one small world, that our borders are arbitrary, that we're all in this together. Going to the moon didn't just teach us about the moon, it taught us about Earth, about ourselves. And there's something deeper, something almost spiritual. We're curious beings. We look up at the night sky and wonder. We ask questions. Where did we come from? Are we alone? What's out there? These questions have driven us since the first humans gazed at the stars. Exploration is part of who we are. It's in our DNA. We didn't stop at the edge of the ocean. We didn't stop at the edge of the atmosphere. And we shouldn't stop at the edge of our planet. The moon is just the beginning. But let's be honest. The path forward is messy. The Artemis program has been plagued by delays. Artemis 2 was supposed to launch in 2024. Then it was pushed to 2025. Now it's scheduled for April 2026, and even that's uncertain. Technical issues keep popping up. A helium seal in the rocket's upper stage. Heat shield concerns on the Orion capsule. Each delay costs money, credibility, and momentum. Critics say NASA is trying to do too much, too fast, with too many unproven systems. They argue for a simpler, incremental approach. Build and test one piece at a time. Others say the problem is the opposite, that NASA is being too cautious, too bureaucratic, that the private sector could move faster. SpaceX, for example, embraces a fail fast, learn fast philosophy. They blow up prototypes, analyze what went wrong, and iterate quickly. NASA, constrained by politics and public scrutiny, can't afford that luxury. Every failure is dissected in congressional hearings. Every cost overrun is headline news. The pressure to succeed on the first try is enormous, which ironically makes success harder to achieve. Here's the brutal truth. The biggest obstacle to returning to the moon isn't technology. It's will, political will, public will, sustained commitment over decades. The Apollo program succeeded because it had clear, unwavering support from the top. Kennedy set the goal. Johnson and Nixon funded it. Congress backed it. The public believed in it. That alignment is rare. Today, priorities shift with every election cycle. Budgets fluctuate. Programs get renamed, restructured, or cancelled. Artemis has survived multiple administrations so far, which is encouraging, but it's fragile. One budget crisis, one political shift, and the whole thing could unravel. Yet despite all the challenges, despite the setbacks and the skepticism, we're closer now than we've been in 50 years. The hardware is real. The Orion spacecraft has flown. The Space Launch System has launched. The landers are being built. Astronauts are training. International partners are committed. The momentum is building. And this time the goal isn't just to go, it's to stay. Imagine standing on the rim of Shackleton Crater, near the lunar South Pole. The sun hangs low on the horizon, never rising more than a few degrees. Shadows stretch for kilometers. In those shadows, temperatures plunge to minus 230 degrees Celsius. But just a few meters away in the sunlight, it's a balmy 0 degrees. This extreme environment is where humanity plans to build its first permanent off-world settlement. Why there? Because those permanently shadowed regions likely hold billions of tons of water ice frozen for billions of years. And because the peaks nearby receive almost constant sunlight, perfect for solar panels. It's one of the most strategically valuable pieces of real estate in the solar system. But accessing that ice isn't simple. You can't just land and start digging. The terrain is treacherous. Craters within craters, boulders the size of houses. No atmosphere means no parachutes for landing. You're coming down on rocket thrust alone, threading the needle in a landscape that's been untouched since the solar system formed. One miscalculation, one computer glitch, and billions of dollars of equipment becomes scrap metal on an airless rock 240,000 miles from home. This is why NASA is taking a methodical approach. Artemis 3, currently planned for 2028, aims to land humans near the South Pole. But before that happens, robotic missions will scout the area, map the terrain in high resolution, identify safe landing zones, test equipment in the harsh conditions. SpaceX's Starship human landing system will need to demonstrate it can deliver astronauts safely to the surface and bring them back. Blue Origin's Blue Moon lander is also in development as a backup option, redundancy, options, fallback plans. This isn't Apollo, where we accepted enormous risk because the Cold War demanded it. This is a different era with different priorities. Let's talk about what living on the moon actually means. In the Apollo missions, astronauts spent at most 3 days on the surface. They lived in the cramped lunar module, essentially a tin can, with just enough life support to keep them alive. They couldn't take their suits off. They ate bland food. They slept in hammocks. It was survivable, but barely. For Artemis, we're talking about weeks, eventually months. That requires real habitats, places where astronauts can remove their suits, breathe normally, sleep comfortably, work productively. NASA is developing modular habitats that can be delivered to the lunar surface and assembled either robotically or by astronauts. These habitats need to protect against radiation. On Earth, our atmosphere and magnetic field shield us from the constant bombardment of cosmic rays and solar particles. The Moon has no such protection. Radiation levels on the lunar surface are about 200 times higher than on Earth. Long-term exposure increases cancer risk and can cause other health problems. So we need shielding. One solution is to bury habitats under lunar soil, called regolith. A few meters of regolith can block most radiation. Another approach is to use water or hydrogen-rich materials in the habitat walls. Water is excellent at stopping radiation. If you have water tanks surrounding your living space, you get protection and a resource reserve. Then there's power. Solar panels work well in areas with constant sunlight, like the peaks near the South Pole. But NASA is also developing small nuclear reactors specifically for the Moon. These fission surface power systems could provide continuous electricity regardless of day or night cycles. They're compact, reliable, and could power everything from habitats to mining equipment to communication systems. The first prototype is scheduled to be tested on the Moon in the early 2030s. Nuclear power on the Moon, that's not science fiction, that's the plan. Transportation is another piece of the puzzle. The Apollo astronauts had the Lunar Roving Vehicle, basically a dune buggy that could travel a few kilometers from the landing site. For sustained exploration, we need something far more capable. NASA is developing pressurized rovers, essentially mobile habitats on wheels. Astronauts could climb inside, take off their suits, and drive for hundreds of kilometers. These rovers would have life support for days or even weeks, allowing extended exploration missions. They could be equipped with scientific instruments, drilling equipment, even small laboratories. Think of them as RVs for the Moon, and we need to talk about suits. The Apollo spacesuits were technological marvels for their time, but they were stiff, bulky, and exhausting to work in. Astronauts described them as moving inside a balloon. Every motion required effort. After a few hours of lunar surface activity, they were drained. Modern suits need to be more flexible, more durable, and easier to maintain. NASA's new Exploration Extravehicular Mobility Unit, or XEMU, is designed with improved mobility, better life support, and modular components that can be swapped out and repaired. Private companies like Axiom Space are also developing lunar suits under contract with NASA. Competition breeds innovation, but here's something most people don't think about: psychology. Living on the Moon isn't just a physical challenge. It's a mental one. You're in an environment that's trying to kill you every second. Step outside without a suit and you're dead in 90 seconds. Explosive decompression, boiling blood, asphyxiation. Even inside the habitat, you're surrounded by rock and vacuum. No blue sky, no breeze, no rain. The Earth hangs in your sky, beautiful but distant. Communication with loved ones has a 3-second delay. Not much, but enough to make conversations feel stilted. Isolation, confinement, monotony. These are real psychological stressors. NASA studies this extensively. They run simulations in isolated environments on Earth. Crews spend months in habitats in Antarctica, underwater labs, desert stations. They study group dynamics, conflict resolution, mental health, who thrives in isolation, who struggles, what activities help maintain morale, what makes people snap. Believe it or not, this research is just as important as rocket engineering. You can have the best technology in the world, but if your crew falls apart psychologically, the mission fails. Let me paint you a picture of what a typical day on a lunar base might look like in 2035 or 2040. You wake up in your sleeping pod about the size of a large closet but private. Artificial lighting simulates a sunrise to help regulate your circadian rhythm. You float through a quick hygiene routine. Water is precious, so showers are short, and the water is recycled. Breakfast is a mix of pre-packaged meals and fresh vegetables from the hydroponic garden. Yes, plants can grow on the moon, inside pressurized greenhouses. Not only do they provide food, but they also produce oxygen and boost morale. There's something psychologically comforting about seeing green, living things. After breakfast, you check the daily schedule. Maybe today you're assigned to the mining operation, extracting water ice from a nearby crater. You suit up, go through safety checks, and head out in the pressurized rover with 2 crewmates. The drive takes 30 minutes across the stark, grey landscape. The sun barely moves at the South Pole, it just circles the horizon. You reach the mining site where autonomous robots have been drilling through layers of regolith. Your job is to supervise, troubleshoot, and collect samples for analysis. The work is slow, methodical, and physically demanding even in the moon's 1/6 gravity. Midday, you break for lunch inside the rover. You discuss the morning's findings. The ice concentration is higher than expected. That's good news. More water means more fuel, more drinking supply, more margin for error. After lunch, you continue working until the shift ends. On the drive back, you watch Earthrise. That never gets old, our planet, so vibrant and alive, hanging in the black void. It puts everything in perspective. Back at the base, you go through decontamination. Lunar dust is nasty stuff, and you don't want it contaminating the habitat. You remove your suit in the airlock, which gets sealed off and cleaned. Inside, you finally breathe freely. The air smells recycled but clean. You spend the afternoon analyzing samples in the lab. The ice you extracted contains not just water, but also trace amounts of ammonia, methane, and carbon dioxide. These aren't contaminants, they're resources. Each molecule tells a story about the early solar system, about comets that crashed into the moon billions of years ago, depositing their cargo in these eternal shadows. Evening comes, though it's hard to tell on the moon where day and night blend into one continuous twilight. You have a couple of hours of personal time. Some crew members exercise. Maintaining muscle and bone density in low gravity is critical. Others video call family back on Earth. Some read, play instruments, or work on personal projects. You choose to go to the observation dome, a small, pressurized bubble with a clear view of space. You sit there, watching stars that don't twinkle because there's no atmosphere to distort them. They're steady, brilliant points of light. The Milky Way stretches overhead like a river of diamonds. You think about the fact that you're sitting on another world, looking at the universe without any barrier between you and infinity. It's humbling, it's terrifying, it's beautiful. Dinner is communal. The whole crew gathers, maybe 8 or 10 people depending on the mission phase. You share stories, jokes, frustrations. Someone mentions they miss pizza. Someone else talks about the upcoming resupply mission from Earth. New equipment, fresh food, mail from home. These little things matter enormously. After dinner, there's a briefing about tomorrow's tasks. Then sleep. Another day on the moon. This isn't fantasy. This is the vision NASA and international partners are working toward: a sustained human presence on the Moon by the mid-2030s. Rotation crews like the International Space Station, but on the lunar surface. Research stations studying geology, astronomy, biology, physics. Testing technologies for Mars, mining resources, maybe even tourism eventually. The Moon as a destination, not just a milestone. But let's address the elephant in the room. Some people think the Moon is a distraction. They argue we should skip it and go straight to Mars. Mars is more interesting scientifically. It might have harbored life. It has an atmosphere, however thin. It has seasons, polar ice caps, ancient river valleys. The Moon is dead, airless, geologically inactive. Why waste time and money on a barren rock when the real prize is the red planet? Here's the counter-argument. Mars is hard, brutally, unforgivingly hard. The journey alone takes 6 to 9 months one way. That's 6 to 9 months of radiation exposure, muscle atrophy, bone loss, psychological stress. Once you arrive, you're on your own. There's no quick abort option. If something breaks, if someone gets sick, if a dust storm damages equipment, you can't just come home. You're stuck there for at least 2 years until the planets align for a return journey. The Moon, by contrast, is only 3 days away. If something goes wrong, help can arrive relatively quickly. It's close enough to test systems, learn lessons, and iterate without betting everything on a single, decade-long mission. Think of it this way. Before you climb Mount Everest, you train on smaller peaks, you acclimate, you test your gear. You learn what works and what doesn't in conditions that won't kill you instantly if something fails. The Moon is our training mountain. Mars is Everest. You don't skip the training just because the summit looks more exciting. That's how people die. There's also an economic argument. Lunar resources could make Mars missions feasible. If we can refuel spacecraft with lunar ice, convert it into hydrogen and oxygen propellant, we don't have to launch all that mass from Earth. Escaping Earth's gravity is expensive. The Moon's gravity is much weaker. Launching from the Moon takes far less energy. You could imagine a future where spacecraft are assembled and fueled in lunar orbit, then journey to Mars from there. The Moon becomes a gas station, a construction yard, a stepping stone. That infrastructure doesn't just help Mars missions, it makes the entire solar system more accessible. Now let's talk about something that sends shivers down my spine in the best way possible: lunar astronomy. The Moon offers observational advantages that are impossible to achieve on Earth. No atmosphere means no light pollution, no weather, no atmospheric distortion. You can build telescopes on the far side of the Moon, permanently shielded from Earth's radio noise. Radio astronomers dream about this. Earth is constantly bathed in radio signals from cell towers, satellites, television broadcasts. It's noise that drowns out faint signals from the early universe. The far side of the Moon is the quietest place in the inner solar system. You could detect signals there that are completely invisible from Earth. Imagine a radio telescope array spread across dozens of kilometers on the lunar far side. It could peer back to the cosmic dark ages, the period before the first stars formed. It could detect exoplanet radio emissions, potentially signs of technological civilizations. It could study phenomena we haven't even imagined yet because we've never had access to that pristine electromagnetic environment. This isn't just about going to the Moon. It's about using the Moon as a platform to understand the universe in ways we never could from Earth. Optical and infrared telescopes benefit too. No atmosphere means perfect seeing conditions. You can observe continuously without waiting for clear nights. And here's something wild. You could build truly massive telescopes on the Moon. On Earth, there are limits to how big you can make a mirror before it sags under its own weight. The Moon's lower gravity changes that equation. You could construct mirrors tens of meters across, far larger than anything feasible on Earth. The James Webb Space Telescope, which cost $10 billion and took decades to build, has a 6.5-meter mirror. Imagine what we could see with a 30-meter or even 50-meter mirror on the moon. And let's not forget neutrino detectors, gravitational wave observatories, particle physics experiments. The moon is a laboratory unlike any other, stable, quiet, with extreme temperature ranges that can be exploited for certain experiments. Scientists are already designing instruments to deploy there. The lunar surface isn't just a place to visit. It's a tool, a resource, an extension of our scientific capability. But we have to be careful. There's growing concern about lunar environmental protection. Yes, the moon has no life as far as we know, but it has scientific value that could be destroyed by careless development. Those permanently shadowed craters contain ice that's been sitting there for potentially billions of years. That ice holds clues about the history of water in the inner solar system, about comets and asteroids, about the conditions when the planets formed. Once we start mining it, once we disturb it, that information is lost forever. Some scientists advocate for preserving certain regions as scientific reserves, off limits to industrial activity. It's a delicate balance. We want to use lunar resources, but we also don't want to destroy irreplaceable scientific heritage. There's also the question of archaeology. The Apollo landing sites are cultural treasures. They're the first places humans set foot on another world. The equipment is still there, the flags, though probably bleached white by solar radiation. The footprints preserved perfectly because there's no wind or water to erase them. These sites tell the story of human achievement. Some argue they should be protected, declared heritage sites, kept pristine for future generations. But there's no international agreement on lunar preservation yet. No laws preventing someone from landing right next to an Apollo site or even disturbing it. As more nations and companies head to the moon, this becomes urgent. We need a framework, rules, treaties before it's too late. This brings us to something crucial that often gets overlooked: international cooperation and competition. Space used to be the domain of superpowers, the United States, the Soviet Union. That was it. Today, the landscape is radically different. China has emerged as a major spacefaring nation with ambitious plans. Their Chang'e program has successfully landed multiple robotic missions on the moon. Chang'e 4 made history in 2019 by landing on the far side, something no one had done before. Chang'e 5 returned samples to Earth in 2020. They're planning crewed missions for the early 2030s and talking about establishing a joint lunar research station with Russia called the International Lunar Research Station. India's Chandrayaan program has also made impressive strides. Chandrayaan 3 landed near the lunar South Pole in August 2023, making India the fourth country to soft land on the moon and the first to land in that region. Japan, South Korea, the United Arab Emirates all have lunar ambitions. The European Space Agency is collaborating with NASA on Artemis. Even private companies are getting involved. This isn't your grandparents' space race. It's a complex web of collaboration and competition, partnerships and rivalries. And here's where it gets politically interesting. Space is becoming contested territory again, but in a different way than the Cold War. It's not about ideology, it's about resources, strategic positioning, and technological leadership. Whoever establishes infrastructure on the moon first gains enormous advantages: access to water ice, prime real estate for bases, control over key landing zones. This raises questions that humanity has never had to answer before. Who owns the moon? Who gets to use its resources? What are the rules? The Outer Space Treaty of 1967, signed by over 100 countries, states that celestial bodies cannot be claimed by any nation. The moon belongs to all humanity. No country can plant a flag and declare sovereignty. That sounds nice in theory, but what about extraction rights? If a company mines lunar ice, who does that ice belong to? The treaty is vague on this. The the United States passed the Space Act of 2015, which allows American companies to own resources they extract from asteroids or the Moon. Luxembourg, the United Arab Emirates, and Japan have passed similar laws. But these are national laws, not international agreements. Other countries might not recognize them. China hasn't signed some of the newer international frameworks. They're developing their own rules, their own partnerships. Russia is increasingly isolated from Western space cooperation, but working with China. You can see how this could create tensions. Imagine a scenario where Chinese and American bases are both near Shackleton Crater, both accessing the same ice deposits. What happens if there's a dispute? There's no lunar police force, no international court with jurisdiction. We need new treaties, new governance structures before conflicts arise. Space law is one of the most fascinating and underappreciated fields right now. The decisions made in the next decade will shape lunar development for centuries. But let's step back from politics for a moment and return to the science, because ultimately that's what drives exploration. The Moon is a time capsule. Its surface preserves 4.5 billion years of solar system history. Unlike Earth, where plate tectonics, erosion, and life constantly reshape the surface, the Moon is geologically dead. What happens there stays there. Impact craters from billions of years ago are still pristine. Rocks from the Moon's formation lie exposed. By studying lunar geology, we learn about Earth's early history, about the formation of the planets, about the violent period known as the Late Heavy Bombardment, when asteroids and comets pummeled the inner solar system. Here's a mind-blowing fact: the Moon and Earth formed from the same event. About 4.5 billion years ago, a Mars-sized object called Theia slammed into the proto-Earth. The collision was so violent that it vaporized huge amounts of material. That debris coalesced into the Moon. This means the Moon is literally made of Earth material plus some of Theia. When astronauts bring back lunar samples, they're studying our own planet's infancy. The Apollo missions returned 382 kilograms of moon rocks. Scientists are still analyzing them, still making discoveries, and we've barely scratched the surface. The South Pole, where Artemis is headed, has never been sampled. Different composition, different history, different stories to tell. There are also mysteries, like the lunar swirls, strange bright markings on the surface that don't correspond to any geological features. They're associated with localized magnetic fields, but we don't fully understand how they formed, or the question of how much water exists in permanently shadowed regions and where it came from, or the exact nature of the Moon's interior structure. We think it has a small iron core, but we're not certain of its size or composition, or the anomalies detected by orbiting spacecraft, mass concentrations called mascons that create gravitational irregularities. Each of these questions requires surface missions, human presence, detailed investigation, and then there's the search for volatiles, not just water, but other compounds locked in the regolith. Helium-3, a rare isotope on Earth but relatively abundant on the Moon, deposited by this solar wind over billions of years. Helium-3 is incredibly valuable for certain types of nuclear fusion reactions. If we ever develop fusion power plants that use helium-3, the Moon could become an energy source for Earth. That's speculative. Fusion power is still experimental, but the potential is staggering. We're talking about clean energy with virtually no radioactive waste. The Moon could power civilization for millennia. But I want to emphasize something important here. For all the talk of resources and economics and competition, the real reason we explore is deeper. It's about who we are as a species. We're pattern seekers, question askers, boundary pushers. 10,000 years ago, our ancestors looked at the ocean and wondered what lay beyond the horizon. They built boats and sailed into the unknown. 500 years ago, explorers crossed oceans, discovering continents, connecting civilizations. 100 years ago, we conquered the air. 70 years ago, we reached space. Each leap expanded our understanding of the world and our place in it. The moon is the next horizon, not because it's easy or profitable or strategically important, though it may be all those things, but because it's there, because we can. Because every time humans have stood at a boundary and looked beyond, we've chosen to cross it. That's our nature, that's our legacy, and it's our future. There's a quote I love from Carl Sagan. He said, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." Think about that. Every atom in your body, except hydrogen, was forged in the core of a dying star billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it came from stars that exploded long before the sun even existed. Their ashes coalesced into planets, into oceans, into life, into you. You are literally made of stardust. And when you look up at the moon, when you think about humans walking on its surface, you're witnessing stardust becoming conscious, reaching out to touch other worlds. That perspective changes everything. It makes our petty conflicts seem small. It makes our shared humanity obvious. It connects us to something vast and ancient and beautiful. The Apollo astronauts talked about this. They called it the overview effect. Seeing Earth from space, seeing it as a fragile oasis in the cosmic dark, changes you. It makes you realize that borders are imaginary, that we're all crew members on Spaceship Earth, hurtling through the void together, that we need to take care of our planet and each other because there's nowhere else to go. And here's the beautiful irony. By leaving Earth, by going to the moon, we learn to appreciate our home planet more deeply. We see its uniqueness, the blue oceans, the white clouds, the green continents. No other world in our solar system looks like that. Mars is a frozen desert. Venus is a hellish pressure cooker. The gas giants are beautiful but utterly inhospitable. Earth is special, rare, precious. And maybe that's one of the most important reasons to explore space, to gain the perspective that helps us protect and cherish what we have. But let me bring this back down to practicalities, because perspective is wonderful, but rockets run on engineering. The Artemis program, as ambitious as it is, faces real challenges that go beyond budgets and politics. There's the issue of sustainability. Apollo was a sprint. Get there first, plant the flag, come home. It wasn't designed to last. After Apollo 17 in December 1972, we walked away. All that infrastructure, all that knowledge, all that momentum, abandoned. We can't afford to do that again. This time we need to build something permanent, something that survives budget cycles and political changes, something that grows and evolves over decades. That requires international partnership. No single nation, not even the United States, can sustain a permanent lunar presence alone. It's too expensive, too risky, too complex, but together, pooling resources and expertise, it becomes feasible. The International Space Station proves this model works. 16 nations cooperating for over 2 decades, maintaining a continuous human presence in low Earth orbit since November 2000. The station has been occupied for over 23 years straight. That's remarkable. And the lessons learned, how to coordinate internationally, how to manage long-duration missions, how to live and work in space, directly apply to the moon. The Artemis Accords, signed by over 40 countries as of 2026, establish principles for lunar exploration, peaceful purposes, transparency, interoperability, emergency assistance, registration of space objects, release of scientific data, protection of heritage sites, extraction and use of space resources. These aren't legally binding treaties, but they're a start, a framework for cooperation. Countries that sign the accords signal their commitment to responsible exploration. China and Russia haven't signed, which creates a divide, but the door remains open. Space is hard enough without making it adversarial. Let's talk about something that doesn't get enough attention, the human element. Who goes to the moon? The Apollo astronauts were all military test pilots, all men, all American. Artemis represents a fundamental shift. NASA has committed to landing the first woman and the first person of color on the moon. The astronaut corps is diverse, representing different backgrounds, nationalities, and expertise. This matters, not just for fairness, though that's important, but because diverse teams are better at solving complex problems. Different perspectives lead to innovation. Exploration should reflect all of humanity, not just a narrow slice. Training for lunar missions is intense. It takes years. Astronauts learn geology so they can identify interesting samples and formations. They practice in simulated lunar gravity using harnesses and underwater training. They study systems engineering so they can repair equipment when things break. They undergo survival training in extreme environments, deserts, underwater, winter conditions. They learn to work in bulky suits with limited dexterity. They train for emergencies, running through scenarios where everything that can go wrong does go wrong. Medical emergencies, equipment failures, communication blackouts, fire, decompression. The training is designed to prepare them for the worst, so that when they're on the moon, they can handle anything. And they're not just pilots anymore. The Artemis crews will include scientists, geologists who can make real-time decisions about where to sample and what to study. Engineers who can deploy and maintain equipment, maybe even medical doctors for longer missions. This multidisciplinary approach means better science and more effective exploration. Apollo astronauts followed checklists created by scientists back on Earth. Artemis astronauts will have the expertise to make discoveries on their own, to follow their curiosity, to ask questions in the moment. But here's a question that keeps me up at night. What happens if something goes catastrophically wrong? Space is dangerous. People die. The Challenger disaster in 1986 killed 7 astronauts. Columbia in 2003 killed another 7. The Apollo 1 fire in 1967 killed 3 during a ground test. The Soyuz 11 crew died during re-entry in 1971. These aren't abstract risks, they're realities. And the more we push boundaries, the more we tempt fate. If an Artemis mission ends in tragedy, what happens? Does the program survive? Does public support evaporate? Do politicians pull funding? History suggests that might be the outcome. After Challenger, the shuttle program was grounded for nearly 3 years. After Columbia, it was grounded for 2.5 years and eventually retired. A lunar mission disaster could set us back a decade or more. And unlike low Earth orbit, where rescue might be possible, there's no cavalry coming if something goes wrong on the moon. You're on your own. That's the reality astronauts face. They know it, they accept it. But does the public? This is why robotic missions remain crucial. Robots don't need life support. They don't get tired or scared. They can work in environments that would kill a human instantly. NASA's Lunar Reconnaissance Orbiter has been mapping the moon in exquisite detail since 2009. The Volatiles Investigating Polar Exploration Rover, or VIPER, was designed to search for ice in permanently shadowed craters, though the mission was unfortunately cancelled in 2024 due to budget constraints. Commercial Lunar Payload Services, CLPS, partners private companies to deliver instruments to the lunar surface. These missions pave the way, reducing risk, gathering data, testing technologies. Japan's Smart Lander for investigating Moon, SLIM, achieved a precision landing in January 2024, demonstrating technology that could allow pinpoint accuracy, landing within meters of a target rather than kilometers. That's crucial for accessing specific sites like a particular crater rim or a scientifically interesting boulder. India's future Chandrayaan missions plan to include rovers and even sample return. The European Space Agency is developing lunar communications and navigation satellites. These aren't competing programs, they're complementary, building a collective infrastructure that benefits everyone. And then there's the private sector. Companies that a decade ago had no space experience are now landing on the moon. Intuitive Machines successfully landed the Odysseus spacecraft in February 2024, the first American lunar landing since Apollo 17, and the first ever by a private company. It tipped over on landing, but it still transmitted data. That's progress. Astrobotic's Peregrine lander encountered a propulsion problem after launch in January 2024 and couldn't reach the moon, but they learned valuable lessons. Failure is part of innovation. The private sector operates differently than government agencies. They move faster, take bigger risks, and iterate quickly. This energy is revitalizing space exploration. SpaceX's Starship is the elephant in the room. It's the most powerful rocket ever built, taller than the Saturn V, capable of carrying over 100 metric tons to the lunar surface, fully reusable, which could reduce costs by orders of magnitude, but it's still in development. Test flights have shown both spectacular successes and spectacular failures, explosions, breakups, but also controlled descents and soft ocean landings. Elon Musk's philosophy is to build, test, fail, learn, and iterate. It's messy and public, but it's making progress. NASA has bet heavily on Starship as the lunar lander for Artemis. If it works, it changes everything. If it doesn't, Artemis faces serious delays. Blue Origin, Jeff Bezos' company, offers an alternative with their Blue Moon lander. It's more conservative in design, building on decades of aerospace engineering. It won't carry as much cargo as Starship, but it might be more reliable in the near term. NASA's strategy of having multiple providers makes sense. Redundancy, options. If one system fails or faces delays, the other can proceed. This is smart management when you're betting billions of dollars and human lives on bleeding-edge technology. But let's zoom out for a moment and consider the bigger picture. Why is all this happening now? Why, after 50 years of going nowhere beyond low Earth orbit, are we suddenly serious about returning to the moon? Several factors converge. First, technology. Computing power, materials science, robotics, life support systems. Everything has advanced dramatically since Apollo. We can do things today that were impossible in the 1960s. Second, cost. Reusable rockets, commercial partnerships, and international cooperation are making space more affordable. Still expensive, but trending in the right direction. Third, geopolitics. China's space program isn't just about science. It's about national prestige, technological leadership, and strategic positioning. When China says they're going to the moon, the United States pays attention. Competition drives progress. It's not the Cold War, but rivalry still motivates. Fourth, resources. The realization that space contains valuable materials, water, metals, rare elements, creates economic incentives. If there's money to be made, investment follows. And fifth, vision. Leaders like Elon Musk talk about making humanity multiplanetary. That captures imagination. It inspires. It makes space feel relevant again. There's also a generational shift. People who grew up watching Apollo are retiring. A new generation that grew up with the internet, with global connectivity, with climate anxiety, sees space differently. For them, it's not about Cold War competition, it's about survival, about backup plans, about expanding beyond a single planet that faces environmental challenges. This generation takes for granted that humans will be spacefaring. The question isn't if, but when and how. Now, I want to address something controversial. Some people argue that spending billions on space exploration is immoral when we have poverty, hunger, disease, and climate change here on Earth. Why go to the moon when people are suffering? It's a fair question and deserves a serious answer. First, the money spent on space doesn't disappear into a void. It employs hundreds of thousands of people, engineers, scientists, technicians, support staff. It drives technological innovation that spins off into other sectors. GPS, weather satellites, medical imaging, water purification, solar panels, cordless tools, memory foam, freeze-dried food, all came from space program research. The return on investment is massive. Second, the space budget is tiny compared to other expenditures. NASA's budget is about $25 billion per year. That's roughly 0.5% of the US federal budget. By comparison, the US spends over $800 billion on defense. The entire Artemis program from start to the first lunar landing costs less than the annual budget for the Department of Defense. We're not choosing between feeding the poor and going to the moon. We could do both if we prioritized differently. The problem isn't that we're spending too much on space, it's that we're not addressing other issues adequately. Third, space exploration addresses long-term existential risks. Climate change is critical, absolutely, but there are other threats. Asteroid impacts, supervolcanic eruptions, nuclear war, pandemics, solar flares, any of these could devastate civilization. By becoming a spacefaring species, by establishing presence beyond Earth, we increase our chances of long-term survival. It's insurance, and it's not instead of fixing Earth, it's in addition to, we need to do both. Fourth, inspiration matters. The Apollo program inspired an entire generation to pursue science and engineering. Kids watched the moon landing and decided to become astronauts, physicists, computer scientists. That human capital drove decades of innovation. Artemis can do the same. In a world of pessimism and division, space exploration offers hope. It shows what humans can achieve when we work together toward a common goal. That's valuable, that's worth something. But let me be clear, space exploration should not be an escape from Earth's problems. We can't trash our planet and then flee to Mars or the moon. That's neither practical nor ethical. The technology and resources required to terraform another planet vastly exceed what we'd need to fix Earth. If we can create a breathable atmosphere on Mars, we can certainly manage carbon emissions here. The real value of space is perspective, resources, and redundancy. Perspective to see Earth's fragility. Resources to supplement what we have. Redundancy to ensure survival if catastrophe strikes. Let's talk about something that fascinates me, the evolution of lunar architecture. The Apollo lunar module was a masterpiece of minimalist engineering. Every kilogram mattered. It had the absolute minimum required for 2 astronauts to land, spend a couple days and return. No frills, no comfort, just function. Modern lunar habitats are different. They're designed for sustained habitation. That means radiation shielding, comfortable living quarters, recreation areas, laboratories, workshops, greenhouses, water recycling, oxygen generation, waste management, everything needed for months or years. Some designs are modular, like Lego blocks. Individual units launched separately and connected on the surface. Others are inflatable, using advanced fabrics that pack down for launch and expand once deployed. Bigelow Aerospace pioneered this technology before the company unfortunately went dormant. Other companies are picking up the concept. Inflatable structures offer more interior volume for less launch mass. They can be surprisingly robust, with layers of fabric and foam that provide better radiation protection than thin metal walls. Then there's the idea of in situ construction, using lunar regolith as building material. Robots could 3D print structures using melted or sintered regolith. No need to bring building materials from Earth. The moon provides everything. Researchers have tested this concept, demonstrating that regolith can be processed into bricks, walls, even glass. Imagine habitats that grow organically, printed layer by layer by autonomous machines before humans even arrive. The astronauts show up to a ready-made base. Science fiction? Maybe. but it's being seriously researched by NASA, ESA, and universities worldwide. Underground habitats are another possibility. Lava tubes, natural tunnels formed billions of years ago when molten rock flowed beneath the surface, exist on the Moon. Some are enormous, hundreds of meters wide, kilometers long. They offer natural radiation shielding and temperature stability. You could build entire cities inside them, pressurize the tube, install airlocks, and you have a protected environment. No need to bury structures under regolith. The Moon did the work for you. Orbital radar has detected dozens of potential lava tubes. Future missions will explore them, assess their stability, and determine their viability as habitats. All of this requires power. Lots of it. Solar panels work, but they're limited by the day-night cycle, except at the poles where sun angles are favorable. Nuclear reactors provide continuous, reliable power regardless of lighting conditions. NASA's Kilopower project developed a small fission reactor that could provide 10 kilowatts continuously for 10 years. That's enough for a small outpost. Scale it up, deploy multiple units, and you can power significant operations. There are concerns, of course. What if a rocket carrying a nuclear reactor explodes during launch? What about waste disposal? These are solvable problems, but they require careful engineering and regulation. Energy storage is also critical. Batteries for when solar panels aren't producing, fuel cells that combine hydrogen and oxygen to generate electricity, producing water as a byproduct. Flywheels that store energy mechanically. Each technology has advantages and disadvantages. The optimal solution probably combines several approaches, creating a resilient, redundant power grid that can handle failures and fluctuations. Then there's the question of food. You can't ship everything from Earth. It's too expensive, too logistically complex. Long-term lunar presence requires growing food on site. Greenhouses using controlled environment agriculture. LED lights tuned to specific wavelengths that plants need. Hydroponic or aeroponic systems that use minimal water. Carefully controlled atmosphere with elevated carbon dioxide to boost growth. Researchers have grown plants in simulated lunar regolith, supplemented with nutrients. Lettuce, tomatoes, peppers, herbs, fresh vegetables to supplement packaged food. But here's the challenge. Lunar regolith contains perchlorates, toxic compounds that are harmless to plants but dangerous to humans. You can't just grow food in raw regolith and eat it. The soil needs processing, washing, or the plants need to be grown in cleaned substrate. That adds complexity. There's also the issue of pollination. No bees on the Moon. Manual pollination or engineered self-pollinating varieties become necessary. These seem like small details, but they matter enormously when you're trying to keep people alive millions of kilometers from Earth. And what about psychological factors? Living on the Moon isn't like camping. You're confined to small spaces. You can't go outside without a spacesuit. No fresh air, no rain, no birds singing. The same small group of people day after day. The same sterile walls. The same recycled air. Isolation and monotony can break people. Astronauts on the International Space Station deal with this, but they're only there for 6 months, and they can see Earth out the window, a constant reminder of home. The Moon offers Earth views too, but it's different. You're not in orbit, you're standing on alien ground. NASA studies this extensively. They select astronauts not just for technical skills, but for psychological resilience, teamwork, stress tolerance, adaptability. They provide communication with family, entertainment, personal space, and structured routines to maintain mental health. Research from Antarctica, submarines, and remote research stations informs these strategies. But there's no perfect solution. Some people adapt better than others. Long-duration missions will test human psychology in ways we can't fully predict. There's also the question of medical care. What happens if someone has appendicitis, or breaks a bone, or has a heart attack? On the ISS, you can evacuate someone to Earth within hours if necessary. From the Moon, it's a 3-day journey minimum, and you need a spacecraft ready to go. Lunar bases will need medical facilities, surgical capability, diagnostic equipment, and training for crew members to handle emergencies. The crew physician becomes one of the most critical roles. Telemedicine helps. Doctors on Earth can guide procedures remotely, but communication lag about 1 to 2.5 seconds each way makes real-time consultation difficult. And here's something we don't talk about enough: death in space. What happens if someone dies on the Moon? Do you bury them there? Bring the body back? The logistics are grim but necessary to consider. Burial on the Moon raises questions about contamination and environmental impact. Returning a body takes up precious cargo space and resources. Some suggest cremation, but that requires energy and produces gases that need venting. There's even discussion of composting at a biological decomposition that recycles nutrients for greenhouse use. It sounds macabre, but it's practical. These conversations need to happen before, not after, tragedy strikes. Now let's shift gears and talk about something more optimistic: lunar economy. What does commerce on the Moon look like? Initially, it's government contracts, NASA and other space agencies paying companies to deliver cargo, build infrastructure, provide services. That's the current model, but eventually private enterprise could sustain itself. Lunar tourism is the obvious first market. Wealthy individuals paying millions for the experience of walking on the Moon. Space Adventures, SpaceX, Blue Origin, and others have expressed interest. The market is small but lucrative. Mining is another possibility. Water ice is mentioned, but also rare earth elements, titanium, aluminum, and other materials that exist in lunar regolith. Launch costs from the Moon are much lower than from Earth, so lunar materials could be exported to space-based industries, satellite manufacturing, orbital construction, propellant depots. This creates a supply chain that doesn't rely on Earth for everything. The Moon becomes an industrial node in a larger space economy. Energy is intriguing too. Solar power satellites in Earth orbit could beam energy down to Earth as microwaves, providing clean, continuous power. Building them from lunar materials and launching them from the Moon might be more economical than launching everything from Earth. This is speculative and requires technology we don't quite have yet, but it's being seriously researched. If it works, the Moon becomes an energy hub for Earth. Scientific research itself becomes an economic driver. Pharmaceutical experiments in lunar gravity, materials, science, astronomy. Universities and research institutions might pay for access to lunar facilities the way they currently pay for telescope time or particle accelerator access. Data, discoveries, and patents have value. Knowledge is commerce. And then there's media. Documentary crews, reality shows, live streams from the Moon. Entertainment has driven exploration before. Think of the public fascination with Antarctic expeditions a century ago, documented in photographs and lecture tours. Lunar exploration captured in high-definition video, distributed globally, generates revenue through advertising, subscriptions, and licensing. The first lunar hotel, whenever it's built, will be a media sensation. All of this sounds optimistic, maybe overly so. The reality is that lunar economy faces enormous challenges: high initial capital costs, long return on investment timelines, technical risks, regulatory uncertainty. Most investors want profit within years, not decades. Space ventures require patient capital, government support, or visionary billionaires willing to lose money short-term for long-term payoff. That limits who can play in this space, pun intended. But there are historical precedents. The Transcontinental Railroad in the United States was economically questionable at first. The Erie Canal, undersea telegraph cables, massive infrastructure projects that required decades to pay off but transformed economies once established. The Moon could follow a similar trajectory. Initial government investment creating infrastructure that private enterprise eventually exploits. It's a proven model. Let me address one more aspect that's critically important: planetary protection. This works both ways. Forward contamination is bringing Earth microbes to the Moon, potentially interfering with scientific study, or, in the extreme case, establishing life where there was none. The Moon is almost certainly sterile, but we don't know that with absolute certainty. Maybe there are microorganisms deep underground, surviving in pockets of water or ice. Unlikely, but possible. If we contaminate the Moon before we search thoroughly, we'll never know. Backward contamination is bringing lunar material to Earth that might contain something harmful. Again, highly unlikely. The Moon has been bombarding Earth with meteorites for billions of years. If there was something dangerous, we'd probably know by now. But Apollo missions still quarantined astronauts and samples for weeks after return, just in case. Modern missions are less paranoid, but protocols exist. We're careful because the consequences of being wrong, however improbable, are catastrophic. There's also cultural contamination, if you will. The Moon has significance to countless cultures, religions, and mythologies. It's been worshipped, celebrated, studied, and romanticized for all of human history. Some people feel that commercializing it, mining it, building on it diminishes its meaning, that we're desecrating something sacred. Others argue that expanding human presence to the Moon honors its significance by making it part of our story, not just an object we observe from afar. This tension won't be resolved easily. It requires dialogue, respect, and probably compromise. Indigenous perspectives are especially important here. Many indigenous cultures have deep spiritual connections to celestial bodies. They weren't consulted during Apollo, they should be now. Their knowledge, their worldviews, their concerns matter. Space exploration can't be exclusively Western, exclusively technological, exclusively utilitarian. It needs to incorporate diverse perspectives, or it risks repeating colonial patterns in a new frontier. That's not just ethically right, it's practically smart. Different perspectives lead to better solutions. If you made this far, make sure to subscribe and give this video a like. And check out this other video at the left side of the screen. The terrifying distance to Alpha Centauri, we will probably never reach it, and understanding why reveals how truly alone we are in the universe. See you there.